That's right. I thought his average was too high, so I decided to lower it.
See?
Good job.
In both cases, you have mg going down. But in the first case, letting
All right, it looks kind of like this, sort of, except their picture's better.
so the acceleration is g over t. The second one is mg
Okay, here we go, everybody. Now, in this particular problem, let's split it up and draw our free body diagram. Okay? So let's draw these two masses separate. Okay, so if I draw M1, and if I draw M2,
Are you doing?
this is number 5, 6.
Okay. Well, 5 is easy, but 6. 6 is not so much.
Well,
No, we need help on number 5.
All right, here we go.
Let's look at it. Oh, no, I think think about it.
Oh, they're trying to help you out in number 6 when they talk about number 5. Okay?
is it
What?
is the like the tension equals mg plus whatever the acceleration is, right?
Yeah.
But is the tension on
No, wait a minute.
plus
No. Tension is not equal to F2G.
plus acceleration or whatever?
Okay, you're right.
But is the tension like if it was just standing still? Tension is on pulley going to be T over 2 for each rope, adding up to
No. 2T. But that's the magic of pulleys.
No. Pulleys make things go around.
All right, here, everybody. Yeah, what I gave you was wrong. Okay, everybody, look. Okay, quiet. Come on. I pull on a string with a pulley attached to a mass down here. All right? Now, this will help you some with the last questions as well, 15. Okay? Now, look. If I pull up on this string, and let's say I pull up with 100 newtons, then how much am I pulling up on the mass with?
5 and 6.
50? What the heck's the pulley for?
200.
Okay, because look what happens. If I separate this out, and here is right here. I've got a tension right here of 100 newtons, but I got a tension over here of 100 newtons. So I'm actually pulling up with 200 newtons. Magic. Woo.
You can create a force, dude.
That's exactly right. I just created a force out of nothingness. Yes. Right?
So this,
Now,
No.
well, you can create forces. There's nothing that says I can't create forces. What physics law permits or restricts me from creating forces?
all of them.
What? Look at that. Woo! I just made a force.
What is the like pair?
But there is an equal opposite force, therefore they can't.
That's exactly right. I pull up with 100 and I create an equal and opposite force in the string of 100 and I wrap it around here so I get two 100s. Yes. I doubled my force.
Right there.
Now look, that because you're all seasoned physics students, that seems like that violates something. But there's nothing in physics that says you can't create a force. Right? You can create forces all the time. There you go, I just made one. Come up here and I'll give you a little push. And you'll feel it. I created a force. The deal is, though, is what is it violating? What does it seem like it's violating?
It seems like it violates conservation of energy.
It violates something like conservation of energy because it looks like I'm getting something for nothing, right?
Right.
The getting something for nothing law is like a violation of conservation of energy. So let's show that it's not a violation of conservation of energy. Because what I'm really doing is I'm applying force over distance, right? I'm applying a force over a distance, which is work, and the work is changing the energy of the object, right?
Oh, that's right.
So now look, if I apply a force, work So what has to happen to my distance? It's cut in half. It only moves a half a meter. So I end up with the exact, at most, the exact same work done here as what I put in there. Okay? So that's the deal. When you pull up on this, what happens is by multiplying the force, you decrease the distance it moves, so the net work is the same and you haven't violated physics and the world doesn't end. Okay?
That's why it takes longer to pull something with a pulley.
That's exactly right. So like for instance, if you're pulling something with a pulley, wow, it's easy to pull it, but you have to pull and pull and pull and pull and pull. How many of you have ever changed a tire on your car and you have to jack the car up?
Yeah.
Do you feel really strong because you're able to lift that car?
Yeah.
Because you can't just go underneath and lift it, now without injuring yourself.
You gotta turn.
But like, yeah, if it's the old kind of jacks, it went like this. To get it to go up anywhere. And the new kinds, they have a little screw in it, but what you do is you have to turn to lift it like that much, right? So what you're doing is the jack is multiplying your force,
I have both.
but at the expense of distance, so the work is the same. In reality, the work is less because the machine is not 100% efficient, and you lose some of your energy or your work, and so it's actually you're putting in like twice as much work as necessary to lift the car, but otherwise you couldn't lift the car, right? So that's the best you can get. Yeah, and keep it lifted, that's right. All right, so here's the deal. Here's where I messed up when I explained this morning, is that this one is going to move down a distance x, but how far is this one going to move then?
Half it.
It's going to move 1/2 x. So wait a minute, if this one accelerates down with a,
1/2 A.
this is going to be,
Oh, 2A. You're right. No, 1/2 A.
this one's going to be 1/2 a of that one. Or you could call this a and that 2a, whichever, you get the same. Yes. All right, so that's where I messed up. That's where I messed up when I explained this morning. I forgot about that. So you've got an M2G here. You've got a tension here. You've got an M1G here and a normal force. And you've got a T and a T. There are two tensions pulling on it. The difference is this, though. When you write this equation, F equals MA in that direction, you get M2G minus T equals MA. Right?
Yes.
Over here, you get 2T equals M1A. But these two A's are not the same.
So we'll just call
This one is half of that one, or this one is double of that one. I don't care which way you do it, you get the same thing. They don't have the same acceleration. So which one? Do you want to make this half of that one? Or do you want to make this double that one?
We have to find the acceleration of M1.
We're finding the acceleration of M1?
Yes.
Then what would be best?
2A on that.
Make this one 2A, because this is A1 and this is A2. But A1 equals 1/2 A2. Right?
Yeah.
No.
Yes?
Yes.
Yeah, we'll just have to.
So what do what do I plug in here to make it A1?
2A1.
I plug this in as 2A1, right? Because I rearrange that, A2 equals 2A1, and I plug that in right here. Okay?
Oh, wait, why you put it right there?
Yeah, you need 2 halves to make a whole.
So that you have two equations and two unknowns.
Which A?
Okay, we actually have three equations and three unknowns. We have 2t equals m1a1. We have m2g minus t equals m2a2. And then we have that a1 equals 1/2 a2. Three equations and three unknowns. And since you're looking for that, you want to get rid of that. So A2 is equal to 2A1. And then you have two equations and two unknowns that you can solve.
And A2 is.
Got it?
Why can't I substitute it?
Why can't you what?
Why can't I substitute
I know,
the
both
equation
of you
in
are
the second
accelerating.
one?
You can. If you substitute this in here, you will get M2G minus M1A1 over 2 equals M2A2. The problem is I have an A1 and an A2.
But then, why can't you substitute the other one in as well? Why can't you say,
Then you can take that one and substitute it in if you'd like. But remember, you're solving for the acceleration of this one. So you want A1. That's fine. You can do it that.
So you can substitute them both?
Yeah.
Okay.
Yeah, you could, any which way algebraically you want to solve that, that's fine. I was just doing it by substituting A in first. If you want to do that first, that's fine.
Our weights are contradictory.
The thing I failed to realize this morning is that they have a different acceleration, and that was my fault.
Then you just plug in like
Yeah, they
That's the weight, sorry.
You got it. You'll have 3 equations and 3 unknowns, and once you get to there, it's just algebra, right? Now, we have done lots and lots of different types of problems so far, and you notice that what I've been doing so far is just, since we've already covered all the different forces in our previous 2 years of physics, right? All I've been doing is essentially just giving you all these different kinds of problems that we're just trying to draw a free body diagram for, because there's always going to be something unusual, something different we haven't seen. And you just take what you know, your knowledge, and draw a free body diagram, and then pick your coordinate system based on the acceleration, and then just work your way through it, okay? Step by step. So the only thing new so far we've learned today is about the pulleys. That was valuable, because I totally forgot that when I worked that.
4 numbers.
Okay, so then just call me, and then I will answer.
We always have 4 numbers. Always.
Okay, so we have this problem. Now, they give us the acceleration.
Is that including gravity?
Yes, if they give you the acceleration, that is the acceleration. And you know, that should make sense, that this acceleration they give you should be less than 9.8. Because it's not in free fall, so it should be something less than 9.8.
It's not the rocket.
That's right. Well, wait a minute, and there is a force upward on this thing, right?
Whoa.
6 Newtons.
Yes, I'm just going to call it F,
No, call
because
it,
everybody's is different.
Call it 6 Newtons.
call it 7.6.
Call it 6, call it 5.6. 6.
I'll call it F. That way I'll please everyone and none at the same time. Okay, here we go. Here's M1. We have an F. We have a T. And we have an M1G, the way I've written it.
Yes.
Those 3.
M1A.
Ah, thank you. No, an M1G,
Oh, but
because
what
gravity's pulling it down.
Some
Oh.
Right. Okay. For this one up here, I'm going to call that M2. We have an M2G. We have a normal. We have a tension. And no friction, right? Our next E homework has friction. So over here,
That was funny.
our coordinate system is positive downward, right? Just a one-dimensional problem. This coordinate system is going to be like this, positive that way, in parallel, and positive that way in perpendicular. Okay?
Wait. I'm not
Just
crying.
so that
Now, wait a minute. Which way is this one accelerating?
that way.
This way. So we need to have our coordinate system match up with our acceleration, right?
Otherwise it's hard.
Otherwise, it's really hard. You make it a lot harder. So here we go. Our F equals ma for this one is going to be a positive m1g minus a t minus an f equals m1a, because that's the sum of the forces ma.
Okay. Thank you.
Okay, this one right here. Let's do parallel. In the parallel direction, we have a positive t
Plus
plus a,
into
there we got a theta, so that's going to be an m2g sine theta, this part, right?
Yes.
Equals m2a. in the perpendicular direction.
They should just cancel.
These two should cancel, and since we don't have friction, that's not going to be a player in the problem, right? Now, when we have friction, this is going to be an important part. We're going to end up with the normal force equaling m2g cosine theta, and that's what our normal force will be, and that will be important for us to know. But in this, yeah, to convert that into friction, right, for our mu mg, or for our mu normal force, okay? But in this case, this doesn't play in our problem at all, but it will.
What?
It will when we have friction. Sorry, it doesn't, but it does. But it will. Tomorrow. No, Friday. Are you confused?
Yes.
Yes.
No. No.
But you're not.
You are, but you're not.
Except for my head.
So there you go. That's all the physics. The rest is just plug and crank.
Okay, the sine theta.
That was easy.
Plug it in, crank it out.
The sine theta.
Thank you.
Break it up.
I got 2, 3, and 4.
Plug it in, crank it out.
Hey, I got a question. I got a question.
Okay. I don't know why you use sine.
And it's time to put your e-homework away because now we're going to talk about dun dun dun.
Friction.
No.
Drag.
What a
Wow.
I know how to make a drag.
Dunce hat? No way. Hey. All right. Okay, everybody, drag. This is our new biggie thing. Okay? Along with something else we'll talk about a little later, which is called slippage. This is our two big new things in Physics C for dynamics. Okay? Okay, first of all, what is drag? Drag is fluid friction from a solid object passing through a fluid. Fluid could be air, fluid could be liquid. Sometimes they just have in the problem what they call is a resistive medium. Some medium that you're moving through. Okay? All right. Now, we've already talked about drag real briefly already. Force drag is equal to dv to the n power. All right? So drag is velocity dependent. Now notice that our static friction before, sliding friction, either static or kinetic, okay? This is friction between two solid objects trying to slide past each other. Notice that it depended only on how hard the two objects were pushed together, the normal force, and what the two objects were like, mu. Over here, B is what the object and the fluid is like. This B is a combination, really. When you get into aerodynamics or fluid dynamics, if you're in mechanical engineering or aerospace engineering, this B will be split up into parts. It will be, one part of it will be what the object is shaped like, and the other part will be what the fluid is like. Okay? In physics, Physics C, we just combine it into one number, because it's one constant. Okay? We're just going to assume that to just be 1. So this incorporates what the object is shaped like and what the fluid is like you're going through. Okay? So the bigger the object, the more jagged and more resistive the object is shaped, non-streamlined, and the thicker the fluid is, the bigger this number will be. So if we're going through air, it's going to be smaller. If you have a streamlined shape like an airplane, it's going to be smaller. Okay? Which is good. We want it to be as small as possible. Or most, well, not always. Can you think of a situation where you want a lot of drag? Where you're
Parachuting.
Yeah, parachuting.
Skydiving.
You don't want a streamlined parachute.
We don't want to.
No good. You want lots of friction, all right? So like a drag chute of some kind. You want lots of friction.
Yeah, but otherwise you'll die.
All right, so here's the deal, everybody.
There's many.
So you fall off ability
Why am I smiling?
How you gonna see it?
because you have a parachute. Okay, right now, your velocity is 0. So you have one force on you, which is mg. So what's your acceleration? G. So your acceleration equals g. And then you fall for a little while, and you're going faster,
This is a little
and you have an mg.
The face is getting straighter.
But you now have drag. What's your acceleration now?
Less now.
Less than g. Acceleration is greater than 0, less than g. Okay, and then you reach this magical spot. On the ground.
That was funny.
You're not right.
Whoa, Alex.
Where the drag force is now gotten large enough because your velocity is bigger still. We call this VT, terminal velocity. You've reached terminal velocity.
Where you're standing still in the middle of the air.
Now, are you standing still?
No, you have a constant velocity.
Are you accelerating?
No.
Okay, your acceleration now is 0, and your velocity equals constant.
Or max. Would it be the max?
And it is also the max velocity. Very good. That's the max velocity you can attain under those situations. Okay?
Unless you change
Unless you change your shape. If you decrease your shape, B goes down, your drag goes down, you go faster until you reach a new terminal velocity. So here's the key. Is it possible to go faster than terminal velocity?
Yes.
Sure it is. So like for instance, let's say that you're falling head first, or say you're falling like a pencil like this, straight down. Your B is going to be less. You're going to have a high terminal velocity. And then if you go whoop like this, you're going to be going faster than the terminal velocity. So it's possible, say like here you are, and you're smiling again because you just opened your parachute. All right, sorry. So now your velocity is greater than your new terminal velocity. Oops, that looks like new.
slow down.
I thought it was what? Oh yeah, because you have to slow down.
So what has happened is your B value, your constant, has gone up. That means that right now your drag force is greater than mg.
So you would have a
So which way are you going to accelerate? You're going to accelerate up. Your acceleration is now up, but wait a minute, you're falling down. So what does that mean?
your velocity.
You're slowing down.
That means your velocity decreases to a new terminal velocity. Now let's draw what this looks like.
Why did you?
Acceleration versus time, and velocity versus time. Okay, this is time equals 0.
Where's N?
This is velocity when you're at, or time where you're at terminal velocity. And this is the velocity when you have your new terminal velocity.
It's just a number. Oh, it's a number that you will have.
Yes.
What if somebody like stapled the ends of your parachute together? You would fall slightly quick. You would fall quicker. Who thinks of those? But at the same time, be falling slower than before. What does that be? You'll fall quicker than before.
All right. B is the constant right here.
Oh, it's going up or
Yeah. Well, that constant has increased, therefore your drag increases. Andy, your question is, what if somebody staples your parachute together? That's called a streamer. Like if you jump out of a plane and you have a parachute and you're coming down and you pop your parachute and your parachute doesn't open properly, it's tangled or whatever, that's called a streamer. And what that does is that increases your drag coefficient, but it doesn't increase it enough. And so you will fall, you'll reach a new terminal velocity, but it will be higher than you wish it to be. Okay? So it's possible to survive that, but chances are you're going to be injured. So if that happens, you have a reserve chute. And so, this is the scary part. What's that?
You have to know how to open one of those.
Reserve chute?
Yeah, 'cause
I
there's some
wouldn't jump out of
people.
a plane without knowing
Okay, how many of you have jumped out of a plane? Yeah, I have too.
Well,
It's fun.
When did you jump out of the plane? Huh?
All right.
She was having.
Shortly after my 17th birthday. So like.
Shortly after your 70th birthday?
17,
Wait, you
it was
look
like
great.
a purposeful jump.
No.
That's right. Yeah, what they tell you is this, is when you jump out of the plane and your chute opens, is you're supposed to look at it. Because a lot of people, they fall out of the plane, their chute opens, and they're really happy because they're not falling so fast anymore. And they forget to look up. That's what I did. I fell out of the plane, fell out. I jumped out of the plane. And the chute opens, and then you're like, wow, this is cool. And then you're like floating around for a second, and you're like, wait a minute, I'm supposed to check to make sure the chute is open properly. So I checked, and it was fine. But if it wasn't fine, that's the scary part. You're supposed to cut it loose and then free fall.
And then you have to rotate. otherwise
Yeah,
you
and then
can
you
hit
have
your
to,
face.
well, you don't have to,
But it's a good
but
idea.
it'll like
Okay, hold
burn
on
your
for a minute.
face
I
as
have
it
to
comes
get
out. So you're supposed to lean back and then pop it and
like
punch it
aliens.
so it comes out. Yeah.
Oh my
Pop it and
God.
punch it. Oh, look at that.
Wait, so you were skydiving?
No, I did not. I did a solo. But when you do a solo, they have a static line to the plane that pulls your chute for you, so that you don't like freak out and just fall. All right, everybody, come on. Hey, we're not done. What's your original acceleration? G. Right here, negative 9.8.
We'll call it negative.
And then what does it do? What does it go to?
Zero.
Does it go linear? Hey, shh.
No.
Does it go like this? Does it go like that? Does it go like that? Okay, and then what? It jumps to one up here and goes like that. Because you're accelerating that way. Instead of that way.
But it's